Hello. So I'm going to speak to you about basically the rest of the story, about efficient coding with spikes and what this implies for the statistics of spike trains, and exactly what signal and what's noise in a population of spiking neurons. So you've already seen this slide. What we show is that there is actually an equivalence between representing information efficiently and setting up a balanced network in order to explain the spikes train statistics. So let me start from basic observations about the activity of neurons in the cortex, which basically led to this balanced network theory. In what you usually observe is that spike trains are asynchronous, irregular, and that you have a lot of variability from trial to trial. So if you record the same neuron over several repetitions of the same stimulus, you will not find the same response, the same spike times, the same spike count. Also, the tuning curves themselves are heterogeneous and context dependent. If you look at the average level of excitation and inhibition received by one neuron, there is a very tight balance between excitation and inhibition. I want to include here a last observation, which I will include later in the talk, which is that despite the fact that these three observations actually relate to high variability in spike timing and non-reproducibility in spike timing, what you do observe is that when you look at plasticity, that is how the weight of the synapse is going to change as a function of pre- and postsynaptic activity, it looks like it's actually depending very tightly on the timing of pre- and postsynaptic spikes. So the question is how you can relate these different observations. But from the first three well-known facts, this leads basically to the population coding approach, where since single neurons are so noisy or variable, and single spike trains also, in order to extract information from this activity, what you need is to sum the response of large population of neurons. And there's a whole theory about how you can do that. And in fact, the code, if we want to simplify a lot, the code is like the mean firing rates of the neurons. That is, it's average activity either over trial or over neurons. And if you look at single spikes, since they are not reproducible from trial to trial, single spikes can be considered as some random samples from that underlying rate. Right. What we do here is we kind of turn the story on its head. So these are, by the way, the student and postdoc that did the work, David Barrett and Ralph. And so rather than starting from the observations about the variability of spike trains and see what that implies for neurocoding, we start from the decoding. We start from the population coding assumption, which is basically, in order to extract information, what the brain is doing is summing from large neural populations. And there's a variable x that the neural population is representing. And we assume that this variable x, an estimate of this variable x hat, will be extracted by a simple linear sum of firing rate, which will make it particularly easy since all you have to do is sum activity and some spikes in order to decode the information. And the efficient coding assumption is that the firing rate that this population is going to find the solutions is the one that will minimize the distance between the variable x and its representation in the population, plus some cost over the firing rate. Right? What does that imply? And how do you do that first? How do you actually generate a network that will find this solution in terms of firing rate? And what does it imply? Right. And what we find, what we will show in the rest of the talk, is that this implies all this observation. Asynchronous irregular spike trains, heterogeneous context-dependent tuning curves, as Christian showed previously, EI balance, but also that LTP depends on the timing of pre- and postsynaptic spikes. And very importantly, that spikes are actually not random samples at all. Right? We'll see, in fact, that even if spikes do look random, if you look at single neurons, at the level of the population, the representation is extremely precise. And the spikes are actually more or less exactly at the right time in order to represent this information, even if you have actually a lot of noise in the system. So let's start with the simplest possible example. We have a single signal x, and we want to represent that single signal x in a spike train of a single neuron. And so here I represent the spikes. And we assume that the decoding is a postsynaptic integration or a linear decoding of that output spike trains. So our variable x hat is just going to be a weight w, a sum of value, times the instantaneous firing rate of that neuron. And the way you can measure this instantaneous firing rate is by convolving these spike trains by an EPSP, by, for example, an exponential of minus lambda t. So it's just basically smoothing the representation, right? Take the spike trains. For each spike, you had an exponential kernel, which you can interpret as an EPSP of a synapse. And we get the red line here, which is just a convolved spike train. The red line is our estimate, x hat, extracted from that spike train. And we want to find basically the dynamics of that neuron such that there is a close match between the input signal x, representing it by the blue line, and its extraction from the output spike train, represented by the red line. So the big question is, where do we place the spikes in order to represent that blue signal? Where should they be in order to ensure a close match between the blue line and the red line? So we start by a cost function, which is the distance between the difference, the squared difference between the variable x and its representation x hat. This is what we want to minimize, and for the moment I'm neglecting the cost. A very simple way of minimizing that function is to use a greedy spike rule, meaning that we can decide to fire a new spike whenever this error here, the distance between x and x hat, with a spike is actually smaller than the error without a spike. All right? So if we do that, the spiking will constantly minimize that error E. So this gives us a very simple firing rule. Whenever the distance between x and x hat plus the contribution of the new spike, w, right, squared, the error with a spike, is larger than the error, is smaller than the error without a spike. So if this difference is smaller than 0, then we should fire a new spike. It's a very simple difference between two quadratic terms, and with a few lines of algebra, we can find this equivalence to this simple rule, which is when the weight w times the difference between x and x hat is larger than a fixed threshold, w squared divided by 2, you should fire a new spike. So basically, you look at the difference between the blue line and the red line, and whenever this difference is larger than half the weight, half the size of a spike, an EPSP here, you fire a new spike. So that's why the red line here is closely tracking the blue line. Okay? And since it's a simple threshold spiking rule, we interpret this decoding error, x minus x hat times the weight w, as the membrane potential of that single neuron. Right? And we interpret this weight term here, this fixed value, as a threshold, a firing threshold. So basically, we get an integrate and fire neuron where we want to fire a new spike whenever the membrane potential exceeds this fixed threshold. And the reason why it's really simply an integrate and fire is that if you look at the temporal derivative of the membrane potential, v dot, the derivative over time, you find that it's simply obtained by applying a Lie term here plus the feed-forward input corresponding to the variable x we want to represent, or more exactly, it's x dot plus lambda x, right? Minus basically a reset mechanism which decreases the membrane potential by w squared whenever a new spike is fired. So what you get at the end is a simple integrate and fire neuron taking x as input and generating spike according to by integrating the threshold and then resetting after each new spike. Okay? So for a single neuron, it's pretty trivial, but it gets more interesting if you consider what's happened if you have a population of neurons rather than just one neuron, right? You can do exactly the same thing with a population of neurons, where you don't have a single input, but you have a collection of different variables that you want to represent, right? You could have j different variables here. And we start by the decoder. We assume that this variable x are going to be extracted from the activity of this population of neurons by a simple linear decoder, so weighted sum of their firing rate. And we define a cost function, which is the distance between the estimate of this variable and these variables plus a cost that depends on the total firing rate, on the firing rate of all the neurons. So we don't want to have too high firing rates. We get the same exact greedy rule, that a new spike is fired whenever this results in a smaller error with a spike than without the spike. So that's the firing rule for neuron J in the population. And we get a membrane potentials that is defined as the decoding error x minus x hat projected on the decoding weights of that neuron. So basically, each neuron here is monitoring the prediction error of the network, of the population, by looking at the difference between x and x hat. And this difference needs to be larger than a fixed threshold, also a function of the decoding weights. Okay? So once we have this firing rule here, we can look at, so basically we have the membrane potential, which is a combination of the decoding error and the costs, and we have the threshold, which is fixed. So if you look at the dynamics of the resulting network, you look at the temporal derivative of the membrane potential of each neuron, you find a simple network of integrated fire neuron with recurrent connections. So the membrane potential has a lead term plus a feed-forward input terms, which represent the contribution of each of these input variable x1 to xj, minus basically a recurrent inhibition term plus the reset, which is a global inhibition in the network. And what this inhibition does is that it implements competition between the neurons, right? They all represent the same variables. And so if one neuron fires, this is going to decrease the error that the population makes. And this decrease in the error is communicated to the other neurons through these lateral weights and prevents other neurons from firing to represent exactly the same information. Okay? So these weights, this lateral inhibition, is ensuring that all the neurons collaborate properly in order to represent the signal X, such that their sum is actually exactly going to give you, or not exactly, but almost exactly give you the original signal X. Okay? In fact, it's not more complicated than the single neuron we had before, except that now, instead of having the same neuron firing all these spikes are fired by different neurons. So if you, for example, you have a population of neurons who have all the same weights, then they will fire at different times. But if you look at the collection of all their spikes, so that's why there's different colors here, but the contribution of all their spikes together will represent the signal exactly. And you already see here that a lot of apparent variability in this spike timing, but in fact, at the level of the population, the representation is very precise. Right? So you can do that with the same weights in all the neurons. More interestingly, you can have different neurons having different weights, and you can track the signal even more closely. Okay? So some neurons here represent increases in the variable x and other decreases in the variable x. But otherwise, it's exactly the same story. What we're able to show is that this simple network is actually solving the quadratic problem, the quadratic optimization problem that we described previously, right? That is, if you look at the match between what would be predicted by the quadratic programming under positivity constraint, this is exactly the firing rate distribution that a network gives you, right? So this simple integrated fire networks solves a problem, which is actually quite hard and nonlinear, of finding the optimal distribution of weights, minimizing this error, knowing that the firing rates have to be positive, which makes it difficult normally for an informatician. Anyway, okay. So that's also, I'm not going to show you that in any details, but if you do inactivation in that network, in those networks, for example, here we implemented this integrator network, which represent I position, and we inactivated part of the neuron, you find exactly the changes that Christian described, right? So the network instantaneously compensates for the loss of half of the neurons in each of the population here. There is no introduction of additional error in the decoding of the network in its representation. So I position would be still controlled perfectly. However, you see a change in the tuning curve. For example, the half of the neurons that have been spared, that have not been inactivated, increase, more or less multiply their firing rate by 2. Right? So they just fire at a higher rate in order to still be able to represent the signal. But I want to go more into details about this, the exact type of spike trains we expect to see here, and how this relates to variability and noise, because it's a topic of the workshop. So think about what's happening, for example, in a network that has all the same weights. So all the neurons here contribute equally, exactly equally, to the representation of one unidimensional variable x. Okay. If you look at, for example, the case of a constant variable x, the population needs to fire regularly in order to present this population. But if you look at the membrane potential of each neuron, because they receive exactly the same input and exactly the same lateral inhibition, it's a toy example here, their membrane potential are all exactly identical. So they rise to threshold, and then they should reach threshold exactly at the same time. So here we cheat a little and assume there's a little bit of noise, a little bit of stochasticity in the system, which there will always be in a biological system. And the slightest amount of stochasticity make one neuron fire first because it reaches threshold first. And as soon as this neuron reaches threshold, it inhibits itself and all the other neurons equally, and all the membrane potential are reset. And then a new integration starts, a new spike is fired and so forth. And so you will have a collection of, like a random chord, like a collection of neurons will fire at different times, exactly at the right time to represent the variable x. However, the order of firing is completely unimportant here, and it's actually completely random, right? So on one trial you see that order of firing, on the other trial that order of firing. If you look at each single neuron, their firing will look completely stochastic. It's only at the level of the population that you will see how regular the representation is. Okay, that's a toy example. Of course, if we use more interesting networks where then all the neurons don't have the same weights, where you represent not a single variable but many variables at the same time, the same result holds, right? You have spike trains that are asynchronous irregular. So every single neuron here have a more or less Poisson distributed spike train. Into details, two neurons, even if here you look at their spiking activity and you find that there's almost zero correlations between the spike trains from different neurons, even if they have very similar tuning properties. What you find is that there is actually correlations in their membrane potential, all right? So in the previous example here, we see all the membrane potential are the same, the spike trains are completely uncorrelated and unpredictable. And here it's the same story for in a more realistic network. What you find is that if you take two neurons with similar selectivity, similar decoding weights, their spike trains are uncorrelated, but their membrane potential are strongly correlated. Or they tend to have this high frequency oscillation here, which come exactly from the same mechanism. And here, there's an underlying integration process, and all these neurons collaborate to it, right? But this correlation is not reflected in the spike trains. So this actually looks similar to some, so for example, the observations made in primary visual cortex. When you look at membrane potentials of two neurons with similar orientation preference, for example, they are actually strongly correlated. They have these high frequency gamma oscillations, but the spike trains are not, or very weakly. But I want to insist on the fact that even if these spike trains are asynchronous, irregular, and have a very high variability, the spikes are not random samples, at least not if you give exactly the same input on different trials. There's zero input noise. The spikes are exactly at the right moment in order to represent that underlying signal. Okay. So if, for example, you take this example, this network here, and instead of using the spike train recorded in a single trial, you take a different spike trail in a different trial. So basically you do, if you have 100 neurons, you do 100 trials, and you take neuron 1 from trial 1, neuron 2 from trial 2, neuron 3 from trial 3. So basically you're treating the neurons as if they were coding information independently from each other. You completely destroy the quality of your representation. You had a lot of variability in the decoder, right? Because all these spike trains might be extremely weakly correlated, with correlations that actually decrease with the size of the network. But these very tiny correlations are enough to ensure that the population is extremely precise. So now the question is, why do we have such a very precise representation at the level of the population? Why is it not like a collection of neurons with independent Poisson noise? And that's because, in fact, they all collaborate, and the membrane potentials, remember the membrane potential monitor the prediction error the system makes. And it's always maintained by the activity of the dynamics of the network. It's always maintained between two tight bounds. These two tight bounds correspond to the threshold and minus the threshold. The threshold corresponds to the decoding weights. So what that means is that the decoding error will never be larger than a single decoding weight in the population. And if you increase the size of the network, the decoding weight has to scale as 1 divided by n, because otherwise your variable would increase with the size of the network. So if you have a fixed variable, you need to decrease the contribution of each single neuron as the size of the network increases. And so that means that as you increase the size of the network, the error decays in 1 divided by n, the number of neurons in your population. If you take the same number of independent of neurons with independent Poisson noise and with the same firing rates, you will find that the error decays in 1 divided by square root of n, because the spikes are not controlled as tightly than here. They are placed more or less randomly, and so you have much more variation in the representation. All right. So I want to finish with how you can learn this representation. So what you can only achieve such a high precision if you have a good fine-tune, if you have a very precise tuning of the connections in your network. And it actually amounts to maintaining a very tight balance between excitation and inhibition in your network. So each membrane potential is a difference between a feed-forward input and a prediction of this feed-forward input by lateral connections in the network. So if these two are tightly correlated, then excitation and inhibition received by each neuron is also tightly correlated. So the system works by ensuring that excitation and inhibition received by each neuron in the population is actually tightly balanced. Okay. So we can ask then, okay, let's say we start from a network with some feed-forward input and some lateral connection matrix. How would this system find the optimal lateral connections? Well, in fact, it can find the optimal lateral connection by ensuring that each neuron in the population learns to decode the variable from the activity of the other neurons. All right? And since this decoding error is reflected in the membrane potential, this is equivalent to teaching each neuron to minimize the square of its membrane potential. So basically, you want to keep the membrane potential in the network as close to, as small as possible. The variance of this membrane potential, which reflects the decoding error, which reflects the balance between excitation and inhibition, needs to be maintained very small. So that's what we do. We define an objective function, which is the sum of the variance of the membrane potential in all the neurons in the population. And it's tightly related to the initial error we assumed the network was minimizing when it was spiking, right? They just do a simple gradient descent on this error. We say, okay, we're going to change the weights in the direction of dE divided by d omega. So it's a simple gradient descent. And we get this very simple rule that you need to change the lateral the connections according to the presynaptic firing rate times the postsynaptic membrane potential. So it's a very simple Hebbian rule, nothing else. Okay? But if you look at it more closely, this Hebbian rule is also predicting the tight dependence of changes in synaptic weights to pre- and postsynaptic spike that you observe experimentally. So if the membrane potential here, by construction, are positive before a spike, because you have to reach this positive threshold, and negative after a spike, because you get reset by twice your threshold. All right? So if you get a presynaptic spike before a postsynaptic spike, you will get a potentiation of the weight. And if you get a presynaptic spike after a postsynaptic spike, you get a depression of the weight. So basically changing the relative timing on pre and post spikes actually change the sign of from LTP to LTD. Right? Okay, so so for example, if we do that with two neurons here, with the same exact weights, then what's going to happen is that initially, because these two neurons do not inhibit each other, and because they receive the same input, they will fire at the same time. You get a lot of spikes here, right? After learning you have learned optimal lateral inhibition between these two neurons, they will fire in different integration cycles, like I described previously.
Are you supposing that neurons are either executor or integrator, or they can?
For the moment, not. The last slide is extending it to networks that separate excitation and inhibition. So in the general case, so this was a very simple example. In the general case, with J inputs, with random weights, you can start from a network that is very bad at representing inputs, and after learning, it becomes very precise as I described previously. Excitation and inhibition initially are not balanced. At the end of learning, they are perfectly balanced. And the spiking activity, the firing rates are initially very high, irregular, and tend to be regular and synchronous. And at the end, the firing rates are very low and asynchronous, right? So that means that this network will actually self-organize into this optimal regime. It's not that we need to put the connections by hand. And finally, we can build networks that respect Dale's law, right? By separating a population of excitatory neurons and inhibitory neurons and receiving some a random set of weights. If the network is large enough, it's asymptotically equivalent to the network without separating excitatory and inhibitory neurons. So it's not a worry. The only thing we have to do is, of course, rectify the weight. So we use exactly the same learning rule, but of course, if this is an excitatory neuron, we don't let its weight go below 0 and vice versa if it's an inhibitory neuron. Right? Okay, so I'm going to pass on this and go to the... I have 1 minute? All right, okay. So I'm going to use the last minute I have. So, of course, this is still a purely representative model, right? It's a model of how you can, the network can represent its input. And you might ask, but what about computation? I mean, is it useful for anything else? The fact is that reaching such a precision in the representation at the level of the population is actually extremely useful when you want to represent, for example, a dynamical system. For example, decision-making or the diffusion models are dynamical systems where you actually need to integrate your input, right? But what you can do, however, is use a very simple self-consistency principle that x hat is very close to x. So you can actually fit back any linear function of x inside the network, right? So for example, you can implement a dynamical system such as this simply by setting up lateral connections within your network, which will typically have opposite signs actually to the connections that are implementing the predictive coding, this optimal efficient coding. And these connections will depend on the derivative of your variable x, right? So I'm not going to give you details about how we do it, but essentially what that means is that there's two sets of connections in these networks, connections that implement the efficient coding and connections that implement dynamics. So let's look at what we can do with this. For example, we can do a perfect integrator here, right? And because there's essentially no noise in the system, if there is no noise in the input signal itself, there will be absolutely no noise or accumulation of noise in the network. So what that means is that any accumulation of noise that you're going to see is accumulation of noise because the input itself to the network is noisy. It's not an internal generation of noise in the network. And you can also implement pretty much any kind of linear dynamics you want. For example, an harmonic oscillator, or differentiator, and so on. So as a conclusion, we've shown that efficient coding implies asynchronous irregular spike times, balanced EI, and non-invariant tuning curve properties, and that this coding can be learned using a very simple Hebbian rule. But it leads us to the very intriguing possibility that balanced spiking networks are actually order of magnitude more precise than previously thought. So it means that the limits in the representational power of an area is not in the randomness of its spiking properties or in some correlations between neurons that are unavoidable because of internal connections or something. The limits is in the input signal itself. So any basically limitation in the input, whether it's because of shared input between neurons or because of random noise added to the input that these neurons receive, all of this noise, input noise, will be translated into correlations between the neurons, either temporal correlations or correlations between pairs of neurons. And that's what we should look at when we look at the limitation in the signal-to-noise ratio of our representation, not, yeah, sorry. Thanks.
Okay, one question maybe? You guys want to fight over it? Go ahead.
So you're talking about the variability, but did you compute the final factor as a function of the final rate and is constant as a function of the final rate?
Yes, so if you have a very small metabolic cost, then the final factor is 1. It's almost exactly Poisson, all right, with a small refractory period. If you increase the metabolic cost, the firing tends to become a bit more regular, and the final factor goes down. And that's because the cost is actually equivalent to a sort of adaptation. So when neurons fire too much, they tend to be less excitable. So after they fire, they will be suppressed for a while. And so that increases the regularity of the spectrums.
Also, did you have a question?
So you guys work in the low noise limit, but you guys study this network also in dual noise.
Yes.
And then, as you were kind of saying at the end, you probably expect correlated variability, etc., etc. What is your interpretation of the experimental literature? Basically, do you think that the correlated variability, which is typically observed, reflects that the system is somehow operating on this large noise regime, or does it reflect the fact that it's operating on a low noise regime, but where you don't know actually what the computation is being performed? Or?
So our interpretation would be that basically these correlations entirely come from limitation in the input itself. There's not an infinite entropy in the input, right? And so, for example, if you have a lot of shared input, that means that there's a lot of neurons representing only a small subset, a small number of signals. And this is because there's less signals than neurons that they will be correlated, and that's this what will limit the representational power. Not internally generated noise, the fact that the input itself is noisy. You don't have a perfect control.